ever get that feeling where everyone's talking about something really important like machine learning and deep learning, and you really want to get it?
Yeah, like beyond the buzzwords.
Exactly. You want to understand the real differences, what makes them tick, but maybe without needing a computer science degree.
Right.
Well, that's pretty much what we're going to tackle today in this deep dive.
Precisely. Our goal is to, cut through some of the hype and give you a clearer picture of machine learning and deep learning. We've looked at quite a bit of material.
Foundational stuff, applications.
Yeah, all sorts, to try and pull out the core ideas for you.
So maybe let's start with that analogy people often use, the circles.
The concentric circles. Good starting point.
Yeah.
So imagine the biggest circle is artificial intelligence, AI. That's the whole grand idea, right? Getting machines to do smart stuff, tasks that usually need human intelligence.
Okay, the big picture.
Then inside that, you've got a smaller circle, machine learning, ML. It's a way to achieve AI. The key thing here is systems learning from data, not being explicitly programmed for every single outcome.
Learning from data.
And then, nestled even deeper inside that machine learning circle, is deep learning.
So deep learning is machine learning.
Exactly. It's a specific type of machine learning. And therefore, it's also AI. But, and this is important, not all AI uses machine learning, and definitely not all machine learning is deep learning.
Got it. So they're related but distinct levels.
Precisely. And what we want to do is unpack the fundamentals and the key differences between ML and DL.
Okay, sounds good. Let's dive into machine learning first then. What's the core idea, like fundamentally?
At its heart, really, machine learning is about creating computer systems that can learn and adapt automatically.
Oh.
Well, from experience,
right.
Which in practice means learning from data. So instead of a programmer writing out exact instructions for every single possibility.
Like, if this, then do that.
Right. Instead of that, the system looks at data, finds patterns, finds relationships, and then uses those patterns to make predictions or decisions about new data it hasn't seen before.
Okay, so it's learning the rules itself, in a way.
That's a great way to put it. It figures out the rules from the examples it's given. It's kind of like learning by example, but on a massive scale.
Can you maybe walk us through the process? How does that learning actually happen?
Sure. Typically, you feed it a lot of data, a substantial data set, and you feed this into specific algorithms.
Algorithms designed for learning.
Exactly. These algorithms are built to detect, underlying structures, correlations, patterns within that data. Once the algorithm has sort of learned these patterns, you have what's called a machine learning model.
The model is the output of the learning.
Yes. And that model can then take new unseen data and apply the patterns it learned to make predictions or classifications or decisions.
Okay. Any examples we might run into every day?
Oh, definitely. Think about Spotify suggesting new songs.
Yeah, Discover Weekly.
Exactly. That system uses machine learning. It looks at what you listen to, what you skip, what you add to playlists, which artists you follow, all that interaction data.
Okay.
By seeing those patterns in your behavior, the algorithm learns your musical taste, and then uses that knowledge to recommend other songs it thinks you'll like.
Makes sense. It gets better over time, usually.
And it's the same idea behind, say, Netflix recommending shows or Amazon suggesting products you might want to buy. They're all using ML to personalize things based on your past behavior.
Right. So you mentioned earlier it's different from traditional programming. Can we elaborate on that contrast a bit?
Yeah, it's a really fundamental difference. In traditional programming, you, the human programmer, write explicit rules. You tell the computer exactly what to do step by step. If you see input X, perform calculation Y, then output Z.
Very defined.
Very defined. With machine learning, you kind of flip it. You give the system the inputs and desired outputs, lots of examples. And the machine's job is to figure out the rules that connect those inputs to those outputs.
So you don't explicitly code the rules? The machine learns them?
Precisely. The algorithm discovers the mapping from input to output from the data itself.
That's quite a paradigm shift. Now, I've also heard this term, feature engineering, especially with traditional machine learning. What's that about?
Yeah, feature engineering. Yeah, that's a really important step in a lot of classic machine learning projects. It's basically where humans, the data scientists or engineers, use their domain knowledge to select and transform the raw data into relevant features that the algorithm can easily learn from.
Features meaning?
Characteristics. So if you wanted to build an ML model to classify pictures of fruit, say,
okay,
you, the human, might decide that important features are things like the fruit's color, its shape, maybe its texture pattern, its size. You'd then extract these specific pieces of information from the images and feed those features to the algorithm.
I see. So you're kind of guiding the machine, telling it what aspects of the data are probably important.
Exactly. You're using human expertise to prepare the data in a way that makes the algorithm's job easier. And the quality of those engineered features often has a huge impact on how well the final model performs.
Right. Makes sense. Garbage in, garbage out, even if the garbage is just poorly chosen features.
Pretty much. Good features are key.
Okay, so that's machine learning, with that human touch and feature engineering often needed. Now, let's transition to deep learning. We said it's a subset of ML. What's the big leap? What makes it deep?
The core innovation, the defining thing about deep learning, is its use of something called artificial neural networks, or ANNs, and specifically ANNs with multiple layers, lots of layers stacked on top of each other. That's where the deep comes from.
Artificial neural networks,
Yeah.
inspired by the brain, right?
Loosely inspired, yes. The idea is to mimic, in a very simplified way, how neurons connect and process information in the human brain. These deep networks allow the system to learn really complex patterns and hierarchical representations directly from the data. Much more complex than what typical shallower ML algorithms could handle.
Okay, multiple layers. That's complicated. How do these networks actually work? How do they process information?
Well, imagine a network of interconnected nodes, like artificial neurons. They're organized into layers. You have an input layer where the raw data comes in, like the pixels of an image.
Okay.
Then you have one or more hidden layers in the middle. This is where the real computation happens. The data gets passed from layer to layer, and at each step it undergoes transformations. It's combined, manipulated.
In complex ways.
In nonlinear ways, usually. And the connections between these neurons have associated weights or strengths. These weights are adjusted during the training process. That's how the network learns.
Adjusting the connections.
Exactly. And finally, there's an output layer that produces the result. Maybe a classification like this image contains a cat, or a prediction.
So the learning is really about finding the right weights for all those connections between the neurons across the layers.
That's the essence of it, yes. The network adjusts those weights based on the errors it makes during training, trying to get closer and closer to the correct output.
Okay. Now, what's a really big advantage of using these deep networks compared to the traditional ML methods we just talked about?
Probably the biggest advantage, and a real game changer, is that deep learning can often perform that feature engineering step automatically.
So it does away with the need for humans to pick the features.
Largely, yes.
Right.
Remember how we said in traditional ML, humans often have to carefully select and craft features like color or shape?
Right.
With deep learning, particularly with things like images or sound, the network itself can learn the relevant features directly from the raw input data. The early layers might learn simple features like edges or corners in an image.
Okay.
Deeper layers then combine those simple features to learn more complex ones like textures, parts of objects, and eventually whole objects. It learns this hierarchy of features all on its own.
Wow. Okay. So it figures out what's important by itself. That sounds powerful.
It is. It removes a huge bottleneck and allows these models to work effectively on very complex, high-dimensional raw data, like images, video, audio, and natural language text, where manually defining features would be incredibly difficult or impossible.
Does this automatic feature learning affect how much data you need?
Absolutely. It's a key difference. Because the network is learning the features itself from scratch, it generally needs a lot more data to do that effectively compared to traditional ML.
More data than the ML examples.
Oh, yeah. While traditional ML models might perform well with, say, thousands or tens of thousands of data points, deep learning models often require millions or even billions of data points to really shine. They thrive on what we call big data.
Big data. Okay, so lots more data needed. What about actually training these things? The computing power.
That's the other side of the coin. Training these deep, complex networks on massive data sets is computationally very expensive. It takes a lot more time and a lot more processing power.
More than standard ML.
Significantly more. Often, regular CPUs, the main processor in your computer, just aren't powerful enough or fast enough. That's why specialized hardware, particularly GPUs, graphics processing units, became so important for deep learning.
The things originally for video games.
Exactly. It turns out their architecture, designed for parallel processing of graphics, is also extremely well suited for the matrix calculations that are central to training neural networks. So, deep learning training often requires powerful GPUs and can take hours, days, or even weeks.
Whereas traditional ML might train faster.
Generally, yes. Traditional ML models are often less complex, work with smaller, pre-processed data, and can frequently be trained much more quickly, sometimes just on a standard CPU.
Okay, that paints a clear picture of the trade-offs. Let's try and crystallize these differences. Can we summarize the key distinctions side by side? ML versus DL.
Sure. Let's recap. Definition-wise, ML is the broader field, learning without explicit programming. DL is a subset using those deep neural networks, kind of mimicking the brain for complex stuff.
Right, and how they handle data input.
ML often uses structured pre-processed data where features might be defined. DL shines with unstructured raw input, like raw pixels or raw text.
Data volume.
ML can often work with thousands of data points.
Yeah.
DL typically needs millions that big data scale.
Training time and resources.
ML, generally shorter training, often okay on CPUs. DL, much longer training times, usually needs powerful GPUs.
What about the human effort involved?
ML can be maybe simpler to get started with, but often needs that manual feature engineering for top performance. DL is more complex to build and tune initially, perhaps, but it learns features automatically. More autonomous learning.
And interpretability. Can we understand why they make a decision?
That's a big one. ML models are often more interpretable, easier to explain. Deep learning models, because of all those layers and complex interactions, are often treated as black boxes. It can be really hard to pinpoint exactly why they reached a particular conclusion.
Interesting trade-off there. Performance.
ML does well on small to medium data sets. DL tends to outperform ML significantly on very large, complex data sets where those intricate patterns can be found.
Okay, and maybe some classic applications for each to make it concrete.
Sure. For ML, think about things like detecting credit card fraud, those early recommendation systems maybe on YouTube or Netflix years ago, identifying spam emails, even chess programs like IBM's Deep Blue back in the day.
Okay, established stuff. And deep learning.
Deep learning powers a lot of the more recent headline-grabbing AI. Things like really advanced chatbots for customer support, the image recognition that lets your phone identify objects or faces, speech recognition in Alexa or Siri.
The virtual assistants.
Exactly.
So thinking about that, what kinds of applications of machine learning, and especially deep learning, that seem like science fiction today might actually become just normal, everyday things in the near future? What new possibilities open up? And maybe, what are the ethical questions we'll need to grapple with as these tools get even smarter and more woven into our lives?